Yeah, that was a great introduction from Carolyn. So she's covered all of the main ideas about dating surfaces from craters, and she's hinted rather strongly at many of the complexities that are there in this topic. But in my talk, I'm going to wind it back a little bit and talk about the main concepts that go into measuring the age from a planetary surface, and especially the moon. And then we will look at the common styles of presenting crater count data that you will come across in research papers. So there are several different styles which in previous decades led to some difficulties in comparison of results from different researchers. But today with newer software tools, we can compare these styles much more easily. Then I'll go a bit into the different kinds of software that are being used for crater count measurements and analysis. And then finally, I will give you a bit of a demonstration of CraterStats 3, which is a recent update of the CraterStats software from last year. It's now an open source project written in Python, and I'll show you a bit how you can use it. So, what are the main constituents that go into a crater chronology model? There's essentially three important things that you have to think about to understand what the age of a surface is. So the first one is that craters form on a surface with a size distribution that depends on the size distribution of the impactor population. So this kind of understanding was looked at back in the 1970s, as Carolyn mentioned, and these plots you see here, they're kind of historical plots. This one on the left from Gault in 1970, he was looking at the problem from a theoretical point of view, so understanding what kind of objects might exist in the solar system that can impact solid bodies, and what kind of crater distributions you would expect them to form on planetary surfaces. So looking at this plot here, you have across the bottom crater diameter on a logarithmic scale. So on the right, these are very large craters. Go to the left, very tiny craters. So you see in crater studies, we're often looking at craters that range over a huge range of sizes. So from 10 to the 3, that's 1,000 kilometers, down to 10 to the minus 5 kilometers, which is centimeter kind of scale. And you can go even further than that. You can identify craters at microscopic scales, and these also exist. So what this plot shows is that for a given time, and you see there are some time isochrons marked on here, 1 billion years, 1 million years, 1,000 years. As time goes on, you expect the density of craters on the surface to increase, and that's the basic idea. And we know that the population of objects in the solar system has a logarithmic slope of approximately -2. So if there is for every 10-meter projectile you find floating around the solar system, there are probably around 100 objects of 10 times smaller, so 100 1-meter objects. And for every 1-meter object, there are probably 100 objects of 10 centimeter size. So here on the right, you see the same kind of study that was done by Neukom, but this time they're looking at the actual craters that are formed on the surface of the moon, rather than thinking about the projectiles that produce them. And what you see here is a collection of measurements of size frequency distributions. So again, we've got crater diameter on the x-axis, and we've got cumulative crater density on the y-axis. So cumulative crater density means that what we're plotting is the number of craters larger than the given diameter against diameter. So at any point here represents all of the craters that are larger than that data point. And you see there are many different data sets on here, a dozen or so. And naturally, they wouldn't all lie along a single line. These have been mutually normalized to bring them to the same line. So different surfaces on the moon have different ages, of course. And so they will have different densities, but the shape of the curve, according to Neukomm's theories, remains constant over time. And so there's the possibility that you can shift all these different measurements up and down until they all join together. And that's what you see here on this plot. So the second component that goes into understanding the accumulation of craters is to connect the crater formation density with the rate of crater formation. So to connect crater density with time. And obviously this depends on the rate of impacts occurring on the planetary surface. And here again, you see some of the important historical plots which were made, or in this case on the left, just a function that first describe this kind of behavior. So you see in this equation from Baldwin in 1971, this is a logarithmic equation. So essentially he's describing an exponential decay in the crater formation rate. And for this early study, he used to measure the time starting at the beginning of the lifetime of the moon. So t equals 0 was 4.5 billion years ago. Whereas you see on the other plots, more recently, we tend to measure time in the opposite direction. So 0 time is today, and 4.5, or we count backwards to 4.5 billion years before today. This one, so actually this one from Hartmann in 1972, this is most like what you see today. So we plot time going forwards with 0 at the present time. This one from Neukomm in 76, he was still plotting things the other way around. So although 0 represents today and 4.5 represents the past, he plotted in the opposite direction. So in Carolyn's talk, I think you saw this same plot, but it was reflected in the x-axis, and so time goes forwards. And in the different forms, so Hartmann's form, he tried to fit the exponential decay into several periods with different half-lives. So you see here that there's a steep half-life, and then it shallows, and then there's a constant cratering rate here. Neukomm did that slightly differently, so he has a single half-life transitioning over into a constant rate, but you can see that essentially the concept is the same thing. And okay, there's still a lot of uncertainty in the exact form of these shapes, as again Carolyn showed towards the end of her talk, but this is less important than understanding the general form of this type of function and how it goes into calculating the ages on the surface. And a third important point to understand, and it's been the subject of discussion over the whole period of crater dating studies, is whether the impact to size distribution could be an evolving function with time. So has the impact of population changed since the time of the early solar system? And of course, that is perfectly possible situation. And so this plot you see on the right is probably the strongest proponent of the idea of changing impact of population with time. And you see, this is Bob Strom, and he suggests that these red curves suggest that they come from the higher up the plot the curves are, the higher the crater densities that you're looking at. And he's suggesting that these high density curves that you see, they come from the early solar system time, have a different shape from the later ones, which so the early ones in red, the later ones in blue. And you see this curved shape in the red ones, and you see the flat shape in the blue ones. And he argued for a long time that this represents a change in the impacting population. However, there's another interpretation that this change could have come about from the fact that the very early crater populations have been altered by surface erosion, and surface erosion affects most of all craters of small sizes. And so the craters at small sizes, which are to the left on this plot, have been diminished in these regions, and that would explain the change from like a flat profile over to a curved one. So that argument has gone on for a long time. It's still of interest, and there was a PhD student at Free University Berlin who was studying this topic only recently, because there was a paper published about 7 or 8 years ago that showed these three curves here that you see on the left in color, like green, red, and blue. And the idea was that the shape should remain the same over different times. So the blue is the older one again, roughly 4.2 billion years ago. The red is the Nectarian period, which is roughly 4.1 billion years ago, and the green is the younger stuff on the moon, about 3.8 billion years ago. And the idea was that this kind of squashing of the blue curve here represented a change of shape between the pre-Nectarian period and the Nectarian period on the moon. So this squashing was evidence that there had really been a change of impactor population. But Chiller-Orgel went on to study this and found that if the data are treated properly, now that there's another complication in counting crater densities, that okay, you assume you count a number of craters on a given area, and the number divided by the area gives you the density. This is fine until you get to a point where you have so many craters on the given area that the craters themselves occupy a large fraction of total area. So when this area occupied by the craters themselves becomes non-negligible, you get an effect that small craters are removed by the larger ones, and their density is reduced. It's possible to analyze this, analyze how the effect plays out on craters of different sizes and correct for it, which is what she did in her work. And she found that if you do make this correction, this blue curve is restored to being essentially the same shape as the red one. So this is not to say that the impactor size distribution hasn't evolved over time, but this particular shape of curve that was thought to be evidence of this is not. So it also appears to be possible that the impactor population has not evolved over time. So these are the three main ideas that you have to grasp in order to really understand everything about how a crater chronology model works. Here I come to the common styles of crater count data presentation. So when you look in different publications, you will see mostly one of these three styles of plots in the older works, and I'll come on to another one that you'll see in more recent stuff. So this one on the left is called the reverse cumulative plot that was favored by Gerhard Neukom. And as I mentioned before, in this plot, you plot the number of craters larger than the given diameter against the diameter, and both on a log scale. And as the surface becomes older, the density of craters moves upwards on the scale. So these different lines you see, they represent different ages of surface. Bill Hartman, he used a different style, so it's not cumulative. He simply plots the number of craters in root 2 bins against the diameter. And he preferred this because it's somewhat more simple to interpret and intuitive. A difficulty about it is that you're confined to the root 2 binning, because if you change the binning size, all the points move. So you wouldn't be able to compare one data set against another. It's slightly more subject to noise, but it's also a very effective method. And one you see on the right is the one that is preferred by Bob Strom. This is probably the most complex to understand. It's called an R plot, a relative plot. And it's essentially the same thing as the Hartman one, but with each data point divided by both the bin width and the diameter to the power of -3. And the idea behind this is that this essentially removes the average slope trend. So you see that both the cumulative and the incremental, they plot with this kind of -2 negative slope. And the negative slope is, okay, we understand that's there, and that's the least interesting part. The most interesting part are the deviations from that average slope. So this kind of plot removes the average slope and plots the deviations from it. So it's a very good kind of plot for studying these deviations. And essentially, you can't interpret it directly as density, but the lines move up on the plot as the density gets higher. The last kind of plot, which was also first suggested back in 1979, like there was a paper published by Arvidsson and many other people who were interested in crater counting at the time, where they tried to standardize the methods that we used for crater data processing. Well, the idea was to standardize it, but in the end they came up with 4 recommended ways of doing it, and the 4 different research groups that were active at the time each chose a different one. So it wasn't really a standardization. But anyway, this one set out some principles in how to at least standardize those 4 different methods. And this plot, which we call differential, it's like the incremental, but you divide the values in each bin by the bin width. The advantage of doing this is that then the plot becomes independent of the binning, and you don't need to be fixed to the root 2 binning that Hartman uses. In some cases, it can be advantageous to use finer binning because you can see some structure in the size frequency distribution that can tell you about modifications of the surface and interesting things that are happening in the geology. It has the advantage, like Hartman's, that each point is independent of the others, so it's like an independent measurement, and that eventually makes the mathematics of treating the age extractions rather easier and more reliable. As I say here, it's easy to discern resurfacing effects. So often, and especially recently, we're interested in what happens to the crater populations after they're on the surface. So of course, you can look at a surface that's several billion years old and it's accumulated a crater population, but not all the craters that ever formed on the surface are still there, because you've got other things going on. If you take Mars, for example, you've got wind erosion or volcanic deposition or dust deposition or other things that can affect the craters that we see on the surface. So most commonly, like if you have a really large crater, nothing happens to it over billions of years, you can still see it. But small ones, they can easily be erased or covered over. And so if you're able to see how the populations change, you know what the population is that you expect after a certain time, and you can see how much has been lost. This can also tell you things about the surface processes and what time periods they've been acting on and what kind of scales they were acting on. So this is also much studied in recent works. Visually, this kind of plot is very similar to the Hartman one. So this is a Hartman one up here. This is a differential plot. You don't see very much different, but they are different in that you can compare plots with different binnings in differential. So going back to the really basic stuff, well, of course, if you want to make this kind of data, the first thing you have to do is sit down and measure all the craters that you see in an area of interest. So here we've got an example figure, like here was an interesting lava flow into a crater on, this one is on Mars. The lava flow front has been mapped out in red here, and we've drawn a blue unit inside this red one, which maps out the area that we're going to count craters in. So typically we try to avoid steep slopes, which would be what you see at the boundary of a lava flow front. We try to avoid that because you can have slope degradation effects that reduce the population there. So we prefer to count on a flat surface. Then you'll notice that in this blue region, there are some other parts which have been excluded. These are to do with secondary crater clusters that I'm not going to talk very much about today, but these are also something you have to worry about, because what we really want to count is the number of primary impacts. So impacts which are just objects falling from space and hitting the planetary surface. But large impactors can throw up material which re-impacts in the vicinity. These are known as secondary craters, and these contaminate an age measurement. So we try to avoid those. They typically form, or often form, in clusters, and so you can recognize them. Not always, though. But inside these excluded regions, there were visible clusters of secondary craters. So you see, with all the red spots inside there, those are the actual craters that were identified, and they are counted, measured, and put in a long list, like you see a small fraction of here on the left. So all you really need to do to make a crater count is to know the area that you're counting over and to measure all the craters inside it. These days we do that inside the GIST system, and you want to extract your diameter measurements, and you want to correct for the image projection and possibly for topographic effects. So if you're counting on an irregular body, but your image projection is to a sphere, then there will be some distortion in the crater diameters that you measure on that image. So if you also have a 3D model of the body of interest, you can make corrections for that. And this kind of processing has been most commonly done by a tool known as Crater Tools, which was written by Thomas Kneissl about 10 years ago at Free University. It's still very widely used. You can download it from the Free University Planetary Sciences website, but you have to know that it only works now with older versions of ArcGIS. So Thomas Kneissl, unfortunately, left science a few years back, and the software is in the state it was when he left. There are alternatives around. So there's a tool called CSFD Tools that was written by Christian Riedel. This was for a particular kind of analysis, this non-sparseness correction that I was talking about with Chilla Orgel's work, to correct for the amount of area occupied by craters in high density regions. This software is available on GitHub. It's a nice tool, but it's not very general tool for everybody to use. So it's a specialized thing. There's another tool called Circle Craters, which was first written by Sarah Braden, and I noticed that Alessandro Frigeri has been making some updates on this. I'm not quite familiar with the point that it's got to, but it's a QGIS plugin, and that has some promise for replacing Crater Tools, which is now becoming out of date. There are also some other tools around, like that JMARS has a capability to measure craters, and I think other people have some other things. But we are at a point where, although most people are using Crater Tools, we really need a nice open source replacement for it. And this tool should probably have some in-GIS functions which do the basic stuff, like allowing you to mark craters with a few points efficiently and add them to a shapefile. Personally, I think it would probably be better. So unlike Crater Tools, which is entirely an add-in inside ArcGIS at the moment, it would be better to have piece of software that can process the shapefiles outside the GIS system now, so that you're independent of what kind of GIS software you use. And then the second part of the analysis is the Cratostat software, which takes this data and runs it through the Crater model or Crater chronology model that you've chosen to use, and brings you to the point of measuring in age from the surface. This software has been going on since 2008. Back at that time, Gerhard Neuken was using a workflow that took measurements from photographic plates. It was quite an impressive thing to see. So they took these digital images that came from different missions and exposed them onto photographic plates, and used a device called a stereo comparator, which could make very precise measurements from these photographic plates to feed into our crater measurements. So obviously, this was a bit before GIS environments were becoming commonly used, and when they did, it made no sense to continue with that. And we transferred this workflow over into Cratostats for the analysis, and Thomas Kneissl developing Crater tools for the measurements itself. In 2011, so a few years after that, we decided to rewrite this Cratostat software to kind of broaden its capabilities. In the beginning, it was just doing the cumulative plots and just replicating the old workflow that was done at Free University. We decided to make it a much more general tool and to incorporate all of the types of analyses that different groups are doing across the world, so that we were able to better compare what we were doing to what other people were doing. Then there have been several scientific developments that have gone on in the time in between as well, and these have been gradually incorporated into the software. So especially looking at resurfacing, that's been a topic of great interest over the last few years. Some work on ensuring that crater populations are spatially random, because this is another way of testing for a primary population and distinguishing it from secondary population. Differential forms and various other statistical improvements. I won't talk in detail about those now. And then last year, I completed a new version of Cratostats that the previous ones would have been written in IDL, which is an expensive piece of software, and it has the danger that at some point we no longer have access to that software, and we no longer have the possibility to update it. So Angelo, among others, and Alessandro were very keen on making an open source version. So eventually they persuaded me to do this, and we got it written in Python, and it's also on GitHub now. The idea this time was to especially get in all of the crater count analysis calculations into a kind of clean reference implementation, so that any future developments have a source to go back to where you can see exactly how these things were calculated. From my point of view, I wanted it to produce graphical output that's consistent with the previous version. People have got used to that now. Of course, I'm now using matplotlib instead of the IDL stuff. And to construct it as an analysis library which can be integrated into other software. So some ideas, it could be integrated into a nice GUI application, or maybe you want to put it into some modeling for other purposes, or you might want to integrate it into a GIS system, something like that. So the new software, you saw that the old one had this kind of GUI interface. The new software reproduces all that functionality using a command line interface. So this is really a stripped down but very pure version of the calculation part of the software. What's updated in the new version, it's got slightly better control of what you can put in the legends and what goes there, layout things, and it makes better quality graphics essentially in the end. And development of new scientific ideas that are going to go into the software, probably I'm going to put them into this version first, and whether I continue to put them into the IDL version, we'll have to see as time goes on. But this one will become the main development software from now on. Okay, a quick demonstration of the utilization of the software. Like what you see down here in the black box is a command line for the new software, Python, CreatorStats, py, and then a series of parameters that specify this particular output block. And here we've got a range of an explanation of each of the parameters. You specify the chronology system, epoch system, equilibrium function if you need it, and then the data overplots. So a -p starts a new overplot. You specify the source file, so here's a sample file here, and then you specify another overplot. So the first overplot is just the data overplot that plots the points. The next one plots an age fit, which is this thing here. That's a Poisson age estimation, the diameter range that you're going to apply that over. Some things to position this little plot nicely, and so on and so forth. There's a second one. Here's another example for a cumulative fit. So this one is a differential fit. This one is a cumulative fit. So you specify cumulative here. Same kind of things. You can specify some subtitles and so on. Resurfacing corrections, things that people will be familiar with if they've used the previous versions. Here's a Hartman plot. You specify chronology system, plot style. You can specify the overlaid isochrons as Hartman does on his plots. You can also output the calculations from the software as a text table, so you can import that into Excel or whatever other software you want to analyze the data with further. And there are some functions to spit out all of the chronology systems that the software knows about. These are the ones that are in there at the moment. Some equilibrium functions that it knows about, and epoch systems that it knows about. You can also add new functions of your own, of course. If you're developing new chronology systems, you can put your own in. And it will also do stuff like list all the different color options and plot symbol options and that kind of stuff. So here's a few example output plots. This is what you can make with these command lines. So here's a chronology function output plot with epochs labeled on there. That's all done automatically. Here's an R plot with showing the epochs in shaded bands with a age measurement superposed. You can make inverted color scheme plots if you'd like to make them for slides with black backgrounds. And here, and just to show that the new development is going into this new software, this is a recent paper that I made with some Chinese colleagues looking at a Chang'e 5 landing site where we were trying to date some very small features. So this was interesting to me because this is right at the limits of what you can do with crater dating. So we were trying to date some rather small impact craters. So these are about 3 to 5 kilometers in diameter by looking at superposed craters on their rims. And if you're interested in more, of course, you can refer to the paper, but using some new techniques that we've brought out over the last few years, that was this Poisson age likelihood method, and combining it with what we call buffered crater counting. That's where you even look at the craters which overlap or intersect your area, and you can make you can improve the statistics by calculating what sizes of craters could overlap the area you're interested in. If you combine all these things, you squeeze the absolute maximum of information out that you can use for age derivation. okay, even with these, you see we get these probability distribution functions out which describe the range of ages that the craters could have, and you see they're very broad things. So we're right on the limit of what can be done here, but it was interesting to see how far you can go with this. So where can you get this software? It's on GitHub. This is the address you find. The installation instructions are there, and they were all working fine until rather recently we decided to standardize the way that the software is installed, and so these instructions that you'll find, they're a little bit out of date. It won't work exactly as it's written here now, but I plan to update this soon. So if anybody is going to use this and would like to contact me with any questions at all about how it works, I'm very glad to help you out with that. And I think I should finish there because I ran out.
Thank you, Greg. Can you hear me now?
Yes.
I had some troubles. Okay, thank you very much for the presentation. I would like to see whether there are questions related to your presentation. If anyone is willing. Maybe Riccardo, Angelo, have you seen questions in the chat?
Well, there are a bunch of them. For example, Pratik is asking for a study area with a maximum crater diameter size of 3 kilometers and minimum of 100 meters. What will be, or is there any constraints on the implementation of the technique? If we have a 25 centimeter resolution image, what will be the lower limit of crater diameter size to be considered valid for crater counting?
Yeah, well, on the technique, there is no limit, but on every actual measurement, you have various things that you have to consider. So if you're talking about 25 centimeters resolution, we normally say you should be aiming for about 10 pixels to properly identify a crater. So that would say 2.5 meter craters should be the smallest that you're looking at. It would be the smallest where you can reliably identify the complete set of craters that are present at that size. But you also need to understand the formation rates. You know, as I showed at the beginning, you need to understand the formation rates of craters at that size, and the general chronology models that are available at the moment. I think probably the one from Hartmann and Daubar, which is the 2016, I think, model for Mars. Are you talking about Mars or the Moon? Well, anyway, for Mars, their model goes down to, I think, 1 meter is the smallest that they consider. On the Moon, I don't think we have a production function that has been elaborated down to those kind of sizes. I think the minimum sizes on the Moon are probably around 10 meters. So at the moment, that would probably be what limits you.
Thank you, Greg. Another question: is there any crater analysis tool that looks at the smoothness of the crater rim when covered with regolith that can help age the crater? So I believe it's asking if we can use the crater degradation in order to age the crater.
So the interesting papers to look at for that are the ones from Alexander Basilevsky. So he's worked on that off and on since the 70s. And this is an interesting way of looking at the ages of very young surfaces, because very small craters, they degrade rather quickly. So you can also try to measure age by looking at the rate of removal of extremely small craters.
And then we have another question is, I assume that the crater distribution on the Moon and other bodies is partially influenced by orbital mechanics. Is there any work done trying to understand the spatial distribution based on this aspect, complementing the current understanding of their surface processes?
Sorry, I didn't quite catch that.
I think it's asking if there is any scaling law that is taking account orbital mechanics with different parts of the solar system for crater production rate, and if the spatial changes in impactor rates versus location in the system.
Yes. Well, yes. That in fact that's the only way to understand the chronology system on Mars, for example, because the only calibrated system that we have is the one from the Moon, because you have to calibrate a chronology system with actual samples. So there are samples from the Moon, and those were used to construct that chronology function that I showed at the beginning. And they calibrate the system. When you want to understand ages on Mars, there are no samples from Mars that can be used. So we take the system from the Moon, and with scaling laws and so on, other considerations about how the impact frequencies and velocities and gravity and other things change the crater formation on Mars. That's how you transfer to another point in the solar system. That's one aspect. Then there's another aspect. There are some people who are interested in how this varies over the surface of the Moon, for example. So the Moon has a leading face and a trailing face. Objects which hit on the leading face are going to, on average, hit with a slightly higher velocity than on the trailing face. And this could slightly adjust the chronology functions as they exist on different parts of the Moon. We don't generally apply that because the effects are quite small, but it's a real effect and it exists.
Okay, we have one last question. What was with the steep down negative slope at young ages on the chronology plot in the last slide you've shown? I believe it's
on this one.
Is that one?
The question is what is the steep,
or the previous one, maybe
this one?
One up from where his mouth is. Yeah, I think this one. Yes. So you have this negative curve, then it's becoming positive and then negative.
Yes. This is an R plot. So the R plot, as I showed at the beginning, and an isochron on an R plot appears with this quite peculiar curve in it. If you remember what they're saying, so if the theoretical size frequency distribution was actually a straight line curve with a -2 slope, then these isochrons here would be exactly horizontal. But these curves, they're representing the deviation from the straight line plot. And this is what is interesting about an R plot, that it enhances the deviations from the straight line function.
Okay, I think we have one last question, then we can go for a small break. And is what happens with the craters that were revealed by GRAIL using gravity data that can't be seen on images? Are those considered into crater counting or not?
Of course, these craters seen by GRAIL are large. They're very large craters. There's no reason why you can't use them in a crater analysis. But when you're doing that, you're trying to date. You know, if you were trying to date hemispheres or something of very large scale on the Moon, these would be a valid thing to use. If you had ideas that maybe the crust was older in some part of the Moon than in another part, you might be able to look at it in this way. I'm not aware of anybody who's been trying to do that, but it could be done.